Now for this lesson, we are going to see how we can perform exploratory data analysis on the Iris dataset. But first, we need to import all the needed libraries for this section. So what are the libraries that we are going to use? First, we are going to use matplotlib, and inside matplotlib, we are going to import the submodule called pyplot. And we are going to import this plot as PLT. So whenever we want to use any function inside this submodule or inside this sublibrary, we are going to write plt dot and then the function. And then we are going to use also numpy, and we are going to use numpy as np. This is the convention. You can import numpy as it is, and then whenever you want to use any function inside numpy, you just write numpy dot. But it's easier to have it as np, so it's easier to write. The same for pandas. We are also going to use pandas for loading the data and perform some analysis on the data. So pandas is very important for this project and for machine learning in general. And we are going also to import cporn. This is a visualization library, as we know, and we are going to use cporn as CNS. This is also the convention. So these are the four main libraries that we are going to use. And then we have sklearn. And as you know, sklearn is a huge library, so it contains so many things. So first we need to import the datasets, and from these datasets we are going to use the Iris dataset. Okay, so this is the first thing we need to import. And then from sklearn also we are going to import the model selection, and from the model selection submodule we are going to import train test split. So this is the only function we need from the model selection. So instead of just loading the whole library or the whole submodule, we just import the needed function. We didn't do this here because we are going to use more than one function from numpy and more than one function from pandas and more than one function from cporn. Okay, so here we are importing train test split, and then we are importing also from the pre-processing submodule inside sklearn the normalizer, and this is very important for normalizing the data, as we are going to see. And we are importing from the metrics in order to decide how well the model performed. We are importing the accuracy score, and for the machine learning algorithm itself, we are going to import the k-neighbors classifier, and the k-neighbors classifier is inside the neighbors submodule inside sklearn. And then from the model selection again, we are importing keyfold. So we can just come here, and instead of just having this line and this line, we can just have something like this. So from model selection, we are importing train test split and keyfold, and we can remove this line. And finally, for our own implementation, from scratch for the KNN, we are going to see that we need to have a class called counter, and this class is inside a built-in library in Python called collections. So you might ask, how I know all this before we started? Basically what I do is that before I start working on the project, I know beforehand that I need numpy and pandas. This is like a given for my project, and most probably cporn, right? And then while I'm working on the project, maybe I will need to have this specific class, right, or this specific function. So whenever I find that I need to import some specific function or some specific module, then I go to the first cell in the notebook and import the needed libraries there. So I have all the imports in one cell. So I go to this cell and import all the libraries I need, and instead of having the importing scattered in the code. This makes your code much easier to read, much easier to document, and for anyone reading your code, they can know exactly what you are doing. Okay, so this is the part for importing the needed libraries. Of course, we need to run this part, and then let's start by performing exploratory data analysis on the Iris dataset. So we are going to use a very famous dataset called Iris, and first we need to understand what are the attributes for this specific dataset, and we have basically 4 attributes. First, we have the sepal length in centimeters, the sepal width in centimeters, the betal length in centimeters, and the betal width in centimeters. So these are the attributes or the features of this dataset. But for now, we will just use 2 features for easier visualization, because visualizing the 4 features at the same time can be a little bit trickier to do. So let's just stick to 2 features for now. And for the class, right, we have the features and we have the class. This is a classification problem. This is a classification dataset. So we have 4 features for each flower, and for each flower we want to decide what is the class of this flower. So the class or the label for the flower can be Iris setosa, Iris versicolor, and Iris virginica. And as you can see here, this is the Iris setosa, this is the Iris versicolor, and this is the Iris virginica. Okay, so we have 3 classes, and for each class we have some features. And we want to look at the beta length, widths, and sepal length and widths, and decide based on this information what is the class for this specific flower. So what we have done right now is very, very important, because when you are working on any machine learning project, you need to understand what are the features of the dataset, what are the different classes for the dataset, and what is the objective of your project. Otherwise, you will be stuck and you don't really know what exactly you are doing or how these features are important for your problem. So this is an overview about how you can understand your dataset. Let's now load the dataset. So how we can load the Iris dataset. Importing the Iris dataset is very, very simple, because we have the datasets class as we said before. We import it here, right? And inside the datasets, if you check, if we just try datasets dot, you will see that we have many functions. But for now, let's check the load functions. As you can see, we have load Boston, load breast cancer, load diabetes, load digits, load files, load iris, and these are toy datasets. So let's go now to sklearn datasets webpage and see exactly what do we mean by that. So let's go. So here we are inside the toy datasets class documentation, and as you can see, sklearn or scikit-learn comes with a few small standard datasets that don't require to download any file from some external website. They can be loaded using the following functions: load Boston, load iris, load diabetes, and so on. So we are going to use load iris, and this is some description for each of the datasets. So if we come here for the iris plans dataset, you will see that we have 150 instances, 50 of each of the 3 classes, and we have 4 numeric predictive attributes and the class, and here we have some information about the attributes and so on. So loading these datasets in sklearn is very easy. It's not that hard at all, and that's why we are calling them toy datasets. By the end of this section, we are going to work on a real world dataset, a dataset that requires cleaning, requires pre-processing, and requires some extra work from your side. But for now, we are going to work on the toy datasets because they are easier to understand, easier to load, and we just want to focus for now on the KNN algorithm itself. So let's go back to the code and understand better how we can load the Iris dataset and how we can perform exploratory data analysis. Okay, so as you can see, we can load the Iris dataset from here, and this is the documentation for this function: load and return the Iris dataset classification. The Iris dataset is a classic and very easy multi-class classification dataset, and this is some information about this dataset, right? And the features, the parameters, what does this function return, and so on. And this is an example on how you can use this specific function, right? As we are doing here. Here we are calling datasets.loadIris, and this will return the Iris dataset, right? So if we just come here and print Iris, as you see, we loaded the data, but of course loading the data just like this can be a little bit hard to work with. So we will just have it in a pandas data frame, right? So now as you can see, we have the data frame. Each column represents one feature, and each row represents one example or one instance. So how we did that? Basically, we just write pandas or BD, right? BD dot data frame. So this is how we create the data frames in pandas, and here we have the data and the columns. So the columns names are Iris feature names plus target, right? So if we just print here, let me show you. If we print Iris, and then I just come here and write feature names, you will see that we have sepal length, sepal width, petal length, and petal width, right? So these are the feature names we have for the columns, and then for the target we have the target. And if we want to load the data itself, we will just write here data, and here we use numpy dot c underscore. So this is concatenation function. So concatenation will just concatenate the data, as you can see here. So if we just write here iris data, you will see the 4 features we have, right? We have here the first row, and this is the first feature for the first row. This is the second feature for the first row, the third feature for the first row, and the fourth feature for the first row, and so on. And if we write print iris target, you will see that we have the class itself. So here we are concatenating the data and the class, right? So this is how we can load the data in Pandas data frame. Now, what is really powerful about Pandas data frames is that we have many functions that can we use to perform very powerful calculations using just one line. We have a function inside Pandas data frame called describe, and using this function we can just see for each feature in our dataset the count, right? So if we have here 150 and then here we have 140, for example, then this means that for 10 examples for the sepal width we have missing data. So using the count we can decide if we have missing data or not. And here we have the mean of the data, right? The mean of this feature, so the average of this feature if it's a numerical. And as you can see, like this is 5.8 and this is 3.0 and this is 3.7 and this is 1.1. So of course the difference between this feature and this feature in terms of the average value is large. So this can be a problem if we are working with a machine learning algorithm that's sensitive to the average value. And then we have the standard deviation, and the standard deviation, as you know from the statistics course or from the statistics section, we know that this is very, very important in order to decide the variability of the data. And here we have the minimum value for each feature. So as you can see, the petal width is 0.1 while the sepal length is 4.3. So there's a huge difference between the minimum here and the minimum here. And the same for the maximum, and we can get the first percentile and the third percentile. So as you can see, using the describe function, we can perform some analysis in just one line, and based on this analysis we can then perform some extra pre-processing, right? Now after that we want to split our data into X and Y, right? Because for any supervised machine learning algorithm we need to have the data as X and Y. So in order to do so, we will just go to the iris data frame, and we have a function inside iris data frame called iloc, and this function is short for index location. So basically, what are the indices we want to get? We want, of course, to get all the rows, right? So this is why we have all here. And then we want to get all the columns other than the last column. So we don't really know beforehand how many columns we want. Of course, we can just come here and write from 0 to 4, right? But it's better to have it as from 0 to -1. And the same for Y. But of course for Y we want all the rows but only the last column. So that's why we have all and then -1. So that's how we split data. Now this is also a data frame. X is a data frame and Y is a series, right? Because we have only one column. If we have one column of the data frame, then this is a series, a Pandas series. So this is X and this is Y right now. Now after that we want to split our data into training and testing. And in order to do so, we use the train test split function. We import it here, right? So as you can see, we imported from the model selection inside sklearn the train test split function. And if you want to read more about this function, you can just hover over here and you can see a quick overview or a quick documentation for this function. Okay, so we have X, we have Y, and we give it the test size, and we give it shuffle or not. So of course we want to shuffle the data. Why we want to shuffle the data? Because imagine that you went to a school and you collected the data from the school. Okay, so you went to the English class, and then you went to the math class, and then you went to the physics class, and so on. So of course, the answers you will get from the English class will be similar to each other, and the answers you will get from the math class will be similar to each other, right? So if you try to train your machine learning model without shuffling the data, then this will lead to bias, right? Because the machine learning model will look first at the math questions or the math answers, and based on this will make some hypotheses or make some decisions, and then it will be confused again when it looks at the English answers and questions, and so on. So in order to make the machine learning learn the representation of your data, it's better to shuffle your data set. So that's why we are using the shuffle. Of course, in some scenarios, for example, the time series data, we cannot shuffle the data because each row in your data in this case will represent a time instance. So you cannot shuffle the time. But other than that, you can shuffle the data. And we are using the random state in order to reproduce the result. So when we run this code again, it will get the same shuffle and it will get the same split. So that's why we have these inputs for this function. And then the output for this function is xtrain, xtest, ytrain, and ytest. Now after that, we can convert these pandas data frames into numpy arrays. So we can do this using numpy.asArray function. So this takes like a list or a pandas data frame and it returns a numpy array. Okay, so this is typecasting. We're converting the pandas data frames into numpy arrays, right? And now if we just run this and run this print line, you can see training set size is 120 samples and the test set size is 30 samples. After that, we want to normalize the dataset. So how we can normalize the dataset? We do this by using the normalizer class in sklearn, and here we have a function inside the normalizer called fit, and we give it the dataset we want to normalize. Okay, so we have the normalizer, and you can check the documentation also for the normalizer and how you can use it, right? Normalizer, and then you call this class or you create an instance of this class, and then we use the fit function inside this class and we give it the data we want to normalize. And as you can see, it normalizes from 0 to 1. So if we have 4, 1, 5, 1, 3, 7, 2, 9, 5, 2, 3, 1, we have the data after transformation. So after we call this scalar or transformer, we use this scalar or transformer to transform the data. And we normalize using the xtrain, the training data, and the same transformation we did or the same scaling we did, we use it also for the test data. And this is very, very important because the test data should represent the actual data in the real world, right? So we don't really have access to this data. So what we have access to is the training data. So this is the only data we can use to normalize the dataset. So we normalize the training data and the test data using the training data. Okay, so as you can see here, this is a sample of the training data before normalization, and this is the same sample of the training data after normalization. So all the numbers are between 0 and 1. And now let's visualize the data before and after normalization. So how we are going to do so? We are going to use the pair plot. So let's run it first to see, and then let's discuss the code. So it will take some time to run. So as you can see, this is the pair plot of the dataset before normalization, and this is the pair plot of the dataset after normalization. So what is the pair plot? The pair plot is basically plotting for each feature, right, all the other features. So as we can see here, the sepal length versus the sepal length, and the sepal length versus the sepal width, and so on, right? So this is a histogram. Okay, so this is a histogram, and we know what do we mean exactly by histogram. And here we have the scatter plot, and here we have another scatter plot, and here we have another scatter plot. And as you can see, the legend or the color represent the class. So you can look at this graph and say, based on the sepal length alone, we can split the data with a good accuracy. And you can make the decision based on the sepal length versus the beta length, right? You can say anything in this region is setosa, and you can have another classifier here or another boundary here to decide that this is virginica and this is versicolor. So by looking at the pair plot, we can understand the distribution of the data. So how we plotted this graph, let's look at the code. As you can see here, first we have this dictionary, and we said before that dictionaries will be very, very important when we go to the machine learning part. We have this dictionary containing 0 is setosa, 1 is versicolor, and 2 is virginica. Because as you know, we had before zeros, ones, and twos. So in order to have, instead of zeros, ones, and twos, to have setosa, versicolor, and virginica, we will use this dictionary. So this is a mapping dictionary. So as you can see here, for the iris data frame, we are replacing the target by di. So for each 0, we will replace it by setosa. For each 1, we will replace it by versicolor, and for each 2, we will replace it by virginica. And for the hue, it's the target. So for the color, it's the target itself. So without this parameter for the pair plot, we will just have this graph, but without any color. Okay, so this is how you perform the pair plot. Just one line of code. And here, in order to have subtitle like this, we will just write before, this is the name of the graph, dot figure, dot subtitle, and we have pair plot of the dataset before normalization. Okay, and the same for after normalization. So if we look at the data before and after normalization, you will see that after normalization, the distribution of the data is much better, right? So if you check here, you will see that the data is scattered, and we cannot really make any decision based on this graph. But after normalization, we can see that the setosa class is far from the two other classes, right? Here, 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 and here. So based on this normalization, we can split the setosa with much higher accuracy than before, than without normalization, right? So this is exploratory data analysis for our dataset. We first started by loading the data, of course, then we normalized the data and we saw the concept of normalization, and then we used the pair plot from Seaborn in order to understand the distribution of the data better. Now, let's continue in the next lesson by implementing the KNN from scratch, right? So let's go.